Hello, this is Jack Jackson. Today we're going to talk about algebraic expressions and some applications. So we're first going to introduce the idea of a variable and different uses of variables, how we can use variables to make algebraic expressions and translate from words to algebra. So algebra is a generalized arithmetic, a generalization of arithmetic, and as such it includes and continues arithmetic in a seamless way. So algebra and arithmetic are kind of the same thing in one sense. They're basic skills that we can work with mathematics. So in one sense, they're just one is a continuation of the other. In another sense, they're also intertwined, because algebra is not just a course that you first take maybe in junior high school or high school or even college. Algebra is a way of thinking and a type of doing mathematics that permeates and is connected in with all of mathematics, starting all the way back in first grade. But if we have to draw a dividing line between what makes arithmetic into algebra, it's the introduction of a variable. As soon as you introduce a variable, now we have algebra. And of course we introduced variables back in first grade, so algebra goes all the way back to there. So a variable is just a letter used to represent a number. Now there are at least three ways of looking at variables. One is solving for unknowns. So one use of a variable is to represent a specific number or perhaps set of numbers that is currently unknown. For example, we might have an equation, x plus 2 equals 5, indicates that we take the unknown number x, and when we add 2 to it, we get the number 5. Well, of course, this one's pretty easy. There's only one such number, so we can solve for x to find that, in this case, x has to be equal to 3. So it's sort of like a mystery. Who did it? Who is that mystery x? And so the idea here is to find out the identity of that unknown value of x. So x stands for a specific number here, or in some case a specific set of numbers, but we don't know ahead of time what it is. So it's unknown, and the whole point of the problem is to find out what it is. Another type of use of a variable is within expressions. So expressions are different use, and in this case the variable can stand for any number. So for example, 3 times parentheses x plus 2 close parentheses is equal to 3x plus 6 because of the distributive property. And that's a statement that's true for any number x, any complex number x, any real number x. And so in this case we don't know or care what x is. We just want to know that these two expressions are equivalent or produce the same output no matter what we put in for x. And so here, completely different than solving for unknowns in a sense, because in solving for unknowns, the whole goal is to find out which x's work, and there may be only a few x's, or in the case of the example we saw above, only one example that works, one answer. But here, this is also an equation, but this is an equation that's always true. Sometimes this is called an identity. And so this identity is true no matter what we put in for x. And so the whole point of working with problems like this would be, say, changing something that looks like the left side, using the distributive property to expand it out into the right side, or going the opposite direction, taking the expression on the right and factoring out the 3 to give us the factored version on the left. And so the point here is not to find out what x is. In fact, there's no way to find out what x is because it could be anything. But the point is to take one expression and rewrite it as a different form. In some cases, the new form is definitely simpler than the other one, so we might call this simplification. In a case like this, it's not necessarily that one is any better or simpler than the other. It's just sometimes you'd rather have it factored and sometimes you'd rather have it multiplied out. Depends on what you're going to do with it afterwards. And we can also talk about evaluating expressions. So a variable can be thought of as sort of a placeholder to stand for a number that can change. And here's really where the word variable really applies, because the x can vary. So we could just take an expression like 3x plus 1, and of course by order of operations this says you first take the input of x, you multiply by 3, and then you add 1 to that product to get the final output. Okay, and this expression 3x plus 1 takes on different values depending on what values we have for the input. So if we let x be 2, for example, we get 3 times 2 is 6 plus 1 is 7. But if we choose a different x, say x is 5, this time we have 3 times 5 plus 1, so that's 15 plus 1 equals 16. So the point here is the x is variable. It can change from one time to the next, and we might put in a particular x that we're interested in, or maybe several of them. So let's take some more look at evaluating expressions. So basically, to evaluate an algebraic expression for some particular value of the indicated variable, we simply replace each variable with a set of parentheses, and in the place of inside the parentheses place the value that the variable is going to take on. And then it's a matter of then the algebra is done. The rest is arithmetic, because now we just have to use our knowledge of the order of operations and grouping symbols so that we make sure we understand the structure of the expression there, the algebraic structure, the order the operations are being applied, and then we could evaluate that. So one of the big things that we have to be able to do is be sure that we're very, very sure that we understand about order of operations and that we understand about grouping symbols. For example, the horizontal fraction line is a grouping symbol. So if we have the expression 2x squared plus 5 over 3x minus 1 and say we want to evaluate that when x equals 4, we replace the x with a 4 in parentheses. Both of the x's, we do that. So now order of operations says we're going to do the squaring first, so 4 squared is 16. Next we're going to do in the top and the bottom separately, we're going to do the multiplication next. 2 times 16 is 32, 3 times 4 is 12. Finally we do the addition and the subtraction, and so we get 32 plus 5 is 37, 12 minus 1 is 11. But notice that I did the top and bottom of this fraction separately, working them down to a single number. I absolutely did not do anything like any kind of canceling out with the top and bottom. That's not allowed here. What you have to do is you have to get these to a single number in the numerator and a single number in the denominator. Then we might be able to reduce the fraction using the fundamental equivalence law of fractions, or we might change it to a decimal. If we use our long division algorithm, this turns out to be 3.36 with the 36 repeating. That is 3.36, 36, 36, 36, 36, 36, 36 forever. Okay. Now, one of the biggest problems that we have working with calculators is keeping track of the proper use of the grouping symbols there. And part of the problem is that many of the calculators, most of the calculators in fact, do not have a horizontal fraction line where you can write it like this. So you'll have to remember to put parentheses around the entire numerator and parentheses around the entire denominator when you replace that with something on the calculator. So keep that in mind when you're doing these exercises. So just for practice, let's do a couple of problems here. So take these two expressions and evaluate them at the indicated values of the variable. And I want you to do this by hand completely, so absolutely no calculator at all. Just get out a pencil and paper and work these out. And when you get it down completely, say to a reduced fraction, then pull out your calculator, work it on the calculator, and check it. And the two methods should match up. So let's go ahead and do this now. Press pause now. Okay, well now you're back, and you should have some answers for these problems. Let's take a look at them. So, doing the problem on the left first, we let x equals 1. We replace x by a set of parentheses with a 1 in it, and that happens 3 places in that expression. Squaring first, 1 squared is 1. Then we multiply. 3 times 1 is 3. 35 times 1 is 35, and 7 times 1 is 7. Then we add, both in the top and the numerator, the top, and then the denominator, the bottom. Do those separately. 3 plus 3 is 6, and 35 plus 7 is 42. and then we can reduce that fraction. 42 is actually 6 times 7, so the 6's will cancel out, leaving a 1 in the top and a 7 in the bottom, and so this is 1/7. If you divide this out with the long division algorithm and made a decimal, this would be 0.142857, 142857, 142857. We get a 6-digit repeating pattern there. Okay, so we try to do this on the calculator. Now, one thing you have to remember is that a horizontal fraction line is a grouping symbol as well as being a divides. But a slanted fraction sign like this, or the divides with the line and the 2 dots, that is not a grouping symbol. So we have to replace the horizontal fraction bar with 2 things. A dividing sign here, which is a slanted fraction sign, but we also have to replace it, put parentheses around the top and parentheses around the bottom. So we need 2 sets of parentheses and that slanted fraction line to replace the 1 horizontal fraction line. Because once again, a horizontal fraction line is a grouping symbol, a slanted fraction line is not. And I just type this in, 3 plus 3 times 1 divided by 35 times 1 plus 7 times 1 square. Make sure I got parentheses around the numerator, parentheses around the denominator, divides in between. Hit enter, and it gave us a decimal version there. And I just said change to fraction, which if you remember is math. Well, enter, and then enter. And that will give us the fraction 1/7. Okay, look at the example on the right side here. 3x squared minus 5x plus 8 over x. Everywhere there's an x this time, we're going to let x be -2. So I put a -2 in parentheses in place of the x. -2 squared is -2 times -2, which is +4. Then we multiply. 3 times 4 is 12. I'm going to think of this as plus a -5. So -5 times -2 is 10, so that's plus 10. And 8 divided by -2 is -4. 12 plus 10 is 22. 22 minus 4 is 18. And that's our final answer. So I can type that in as 3 times parentheses -2 square, close parentheses square, minus 5 times open parentheses -2 close parentheses plus 8 divided by open parentheses -2 close parentheses, enter, and sure enough I get 18. Now, mathematics is a multifaceted, diverse field. It's used for lots and lots and lots of different things. And one of the main reasons we study mathematics is because it strengthens the mind's ability to reason. So developing one's mathematical abilities has far-reaching benefits throughout your life. So the main reason we study mathematics is to develop these thinking skills, these things that we talked about earlier in the standards for mathematical practice. And even at its highest form, mathematics is an art form. Research mathematicians study and develop and discover and create new mathematics for its own sake. They don't really care if it's useful for anything else or not. It's just cool. It's mathematics. It's awesome. It's like an art form. Same reason somebody does a painting. Ultimately, usually, there may be a commercial painting or a commercial use for a painting or for an advertisement or something, but oftentimes paintings are just done because they're art. They're cool. You know, people like to do them. Same thing is true for mathematics. But for most folks, the main benefit for mathematics is seen to be its ability to describe and model the world and its utility as a problem-solving tool. So that's kind of going to be our focus of a lot of what we do in this course, is going to talk about how we can use mathematics to describe and model the real world, and that could be all kinds of things in everyday life, and maybe not so everyday life, but all kinds of applications. And we want to use this to help us solve problems, and we're going to develop some problem-solving abilities. So a first step we might make in connecting mathematical concepts to applications in a variety of real-world settings is we will learn how to convert ordinary English words and phrases and sentences into algebraic expressions, equations, and inequalities. And let's start with just a few basic words and talk about how they relate from algebra to words. Actually, the words are part of the algebra. The formulas and expressions are part of the algebra as well. So the operation given by this little cross here, plus sign, is called addition. Okay, so the English words for that might be addition or add, more than, sum, increase, increased by, plus. There may be some others. And so I have some examples here on the right. Add 2 to x. That would be x plus 2. 3 more than a number. If x is the number, that would be x plus 3. The sum of 2 and a number. Again, if x is the number, then that expression would be 2 plus x. Increase a quantity by 5, x plus 5. 6 plus a number, 6 plus x. So notice how we were able to take something that was in words and then turn around and write it in algebraic symbols. Another operation, of course, is the little horizontal line there for subtraction. And the English words would be subtraction, subtract, less than, less, difference, decrease, decrease by, minus. So let's look at these. Now, as I go through these, be sure that you pay attention to the order of the subtraction. It's not such a big deal in addition because addition is commutative, but subtraction is not commutative. A minus B is not the same as B minus A, so we want to make sure that we get the order right in the way we translate these words into expressions. Subtract 2 from x. That would be x minus 2. 3 less than a number. That would be x minus 3. 3 less x. 3 minus x. I don't particularly like that one, but that's I've seen that. The difference of 2 and a number. 2 minus x. Decrease a quantity by 5. X minus 5. 6 minus a number. 6 minus x. Now, when we're trying to put a sentence together, what's the one part of speech that's always in every sentence? And the answer is, well, it's a verb, right? And so if we want to actually make a statement mathematically or any other way, we've got to have a verb in our sentence. Okay? And so if I just write a bunch of numbers on a piece of paper, if I never write down something that's a verb, I haven't made a statement. I've just written down a bunch of numbers. Now, we have different symbols that relate to certain verbs. We've seen is an element of and so forth. Well, one of the biggest ones is the equal sign. Okay, equals, is equal to, equality, same, and the be verbs is, are, was, were, will be, and so forth. So those all kind of relate to equality. So we could say a number equals 5, x equals 5. Two quantities are the same, x equals y. The product of two numbers is 4. The product of two numbers would be x times y, is the equals, and then 4 on the other side. So when you're translating from words to algebraic symbols, when you get to something like a be verb, is, are, was, were, that's going to be your equal sign usually. Okay, let's look at a couple more here. Multiplication. Actually, we have several different notations. One is a raised dot, one is this cross like this. Multiplication, multiply, product. Of, the word of is multiplication, particularly when you're dealing with fractions and percentages. Twice is specifically multiplying by 2. Thrice is multiplying by 3. Times is multiplication as well. So here's some examples. Multiply two quantities, x times y. So one quantity is x, the second quantity is y. Then multiply the two quantities, x times y, or just xy. 3 multiplied by a number, 3 times x. The product of 6 and a number, 6 times x. 1/2 of a number, that's 1/2 times x. X is the number. 30% of x. Well, 30%, the first thing we do is rewrite it as a decimal, so that's 0.3. And then the of is times, and then the x, so it's 0.3 times x. Twice a number, 2x. Thrice a number, 3x. 4 times a number, 4x. Divides can be written with the horizontal line with the 2 dots, a slanted line, or horizontal line. The horizontal line is also a grouping symbol for a fraction. The slanted line and the line with the 2 dots are not grouping symbols. Words that you might see in English would be division, divide, quotient, per, ratio, to, or I might say something about breaking apart or separating into equal parts. So divide 6 by x, 6 divided by x. The quotient of x and 5, x divided by 5. Miles per hour, that's miles divided by hour. I probably should say mi, because usually m is meters. Miles is mi. Percent, per cent. Per means divided by, cent means 100. So literally the percent sign means divide by 100. I should say divide by 100. The per part of this percent is divide by. So if I have 30%, that literally means 30 divided by 100. The ratio of 6 and a number is 6 divided by x. 3 to 5, that's a ratio, 3 colon 5, but it also could be thought of as a fraction, 3 divided by 5. Break x into 5 equal parts, well, each part will be of size x divided by 5. Exponents, we have words there, actually 3 words that are going to mean the same thing: exponent, power, and logarithm. Word logarithm might be new to you, but it really means the same thing as an exponent or a power. Squaring and cubing are specific powers, 2 and 3 respectively. So if we say x to the 5th power, that's written as x superscript 5. We read that x to the 5th power. A number with exponent 7, that would be x to the 7th power. A number with logarithm 2, x to the 2nd power. Square a number, x to the 2nd power. A number cubed, x to the 3rd power. So hopefully in this relatively short video you've been able to talk about some basic things here. Most of these you've probably seen before, but after practicing this material you should be able to describe uses of a variable and understand the difference between, say, solving an equation versus manipulating an expression versus evaluating an expression. Understand the structure of algebraic expressions, whether those expressions are being delivered to you in the form of a word or a formula of some kind. You should understand the order of operations and grouping symbols so that you understand the structure of it. Then, of course, if you understand that, you should be able to evaluate algebraic expressions both with and without a calculator. And you should know how to do some basic operations on a calculator. We actually introduced that in another video, and then that applies here to evaluating expressions. And you should be able to convert between verbal expressions and algebraic expressions, at least for some fairly simple examples.